The concepts I discuss in this video are fairly straightforward, but are absolutely central throughout data science and machine learning. The ideas of conditional probability and event dependence that we will be looking at are used in all sorts of different places, such as Bayes classifiers, neural networks, and many other applications. I'm going to be upfront with you and admit from the start that everything that we will be doing in this video can be dealt with by an application of those four equations that you see in front of you right now. Now, my brain does not work this way. I could, yes, of course, force those equations into my memory banks and then apply them in an exam situation such that I would then pass the exam. But I do not personally feel confident that such an approach would create an understanding in my mind of what in fact is going on. And if you feel the same way about it, if your preference is to have a deeper understanding which has the side benefit of providing a perhaps simpler way of visualizing and calculating the required probabilities both under exam and real world situations, while simultaneously creating a deeper understanding of what is going on, then carry on watching. So those equations, yes, they are what they are. They can be memorized, they can be applied, they can be a route to success in exams and elsewhere, but that is not how I think. And if you feel the same way, then this video is for you. So instead of those equations, we're going to sketch out a probability tree for two events, the first of which is event B, and that is followed then by event A. Let's start with the basic structure of the tree. We have a main branch that splits into two, which represents the first event B. Each of those branches then split again, representing the second event A. This structure will allow us to map out all the possible combinations of outcomes for events B and A. Next, we label the ends of the branches, which we will call nodes, starting with the node at which B occurs. The other node for event B is indicated with B superscript C, where the C stands for the complement of B, and that is the instance in which B does not occur. So you can think of B superscript C as not B. Then we have event A, which is dependent or conditional on event B. And event A may or may not occur depending on whether event B does or does not occur. So we label the four terminal nodes in this particular tree as A, not A, and then a repeat of those for the condition in which B did not occur. Now let's add our first probabilities. On the left, we have the probability of B occurring at 0.6. That means that the probability of B not occurring, or the probability of B superscript C, has to be 0.4. Notice that the two probabilities sum to 1 because they cover all the possibilities for event B. Moving along the tree to the right, we now consider our second event A, which you will recall is dependent or conditional on events B occurrence or non-occurrence. So we have four particular outcomes here depending on whether B did or did not occur. From the top, we have the probability of A given B at 0.8. And if you have not seen that particular notation before, just be aware that that vertical bar is read as given that, and it is indicative of a conditional probability. Next, we have the probability of A superscript C, which is the probability of A not occurring given that B did previously occur, and that has to be 0.2 because A can either occur or not occur, and therefore the two probabilities must add up to 1. The lower part of the tree is where B previously did not occur, and if that is the situation, then the probability of A given that B did not previously occur is 0.3 in this example. And finally, because those two branches in the lower section of the tree must add up to 1, we have the probability of A not occurring given that B did not occur at 0.7. Let's now label the probabilities that we have so far and consider where we obtain them from. On the left-hand side, the probabilities of B occurring or not occurring are called unconditional probabilities. In this analysis, which is isolated to events B and then A, B does not have any dependency within this particular analysis. So those probabilities are referred to as unconditional probabilities. They are the probabilities on the left-hand side of your decision tree where it begins. Next, we have the probabilities of A or not A occurring, and those are called, for obvious reasons, conditional probabilities. In this system, in this analysis, A depends on whether B did or did not previously occur, and therefore those probabilities are referred to as being conditional. The sources of those probabilities that we have entered into the probability tree so far are either empirical or subjective or a priori, which means that they were obtained from historical data or from professional judgment or on the basis of theory. And in fact, it is the case that there are only 3 probabilities from the ones that we have written down so far that are required in order to populate the entirety of the tree so far. And those are the unconditional probability of B occurring at 0.6. So that would have to be obtained from empirical, subjective, or a priori sources. Next, we would need the probability of A given B at 0.8 from one of those same sources. And then finally, we would need the probability of A given that B did not occur at 0.3. And from those 3 initial probabilities obtained from one of those sources, we would be able to set up and populate this tree to the extent that we have it at this point. Now we are in a position to be able to calculate the probabilities of each of those 4 terminal nodes, and those are done by using the tree as your route map. So, for example, the first terminal node probability, which is the probability of A and B occurring, is calculated as 0.8 times 0.6, which equals 0.48. And you can see that those probabilities are simply obtained by following back to the source the probability of A given B at 0.8 and the probability of B at 0.6. We apply exactly the same principle to the other 3 branches, and we label them as the joint probabilities. We also note that the joint probabilities are calculated in contrast with the empirical, subjective, or a priori sources mentioned earlier. We then complete the tree by calculating the overall probabilities of A occurring or not occurring given the probabilities we've been working with so far. So we calculate the overall probability of A by identifying each of the branches at which there is an A occurring, and those are the first and the third branches in our probability tree. So it is simply a matter of adding the 0.48 for the probability of A and B to the 0.12 for the probability of A and not B occurring, giving us an overall probability for A of 0.6. The probability of A not occurring must be 0.4, but we can check that by adding up the probabilities for all of the branches at which we have an A superscript C, and that is the second branch at 0.12 and the final branch at 0.28, giving us a sum of 0.4. Those overall probabilities for A and not A are alternatively referred to as unconditional probabilities, which in a sense brings us back to the start, but another perhaps more common label is referring to them as marginal probabilities. We note that those final probabilities for A and not A are calculated in the same way that the joint probabilities are calculated, and in contrast with the earlier probabilities obtained from external sources. And to wrap up the video, we label the parts of the tree that indicate that we have mutually exclusive and exhaustive events, which means in the case of mutually exclusive that only one of the events, not both, can occur. And in the case of exhaustive, that means that those outcomes together represent all possible outcomes. The unconditional probabilities of B and not B are mutually exclusive and exhaustive, as are the joint probabilities, as well as the unconditional or marginal probabilities of A on the right-hand side. The ones to watch out for are the conditional probabilities in the middle. There you need to take a little bit more of a granular analysis and understand that you cannot simply go straight down that part of the tree, adding up all those probabilities and expect to get to a total of 1. Those represent situations in which we have different branches of reality. For example, if B occurs, then within the universe in which B did occur, A may or may not occur. So if we look at the two branches coming from event B occurring, those two indeed are mutually exclusive and exhaustive. However, going further down, the not B node itself represents a separate reality that cannot coexist with B occurring. And once again, there we have events A and not A together representing a sample space in which the two probabilities add up to 1. And that concludes our initial overview of probability trees. If you made it this far in the video, that's awesome. Well done. And I applaud your interest in the topic. And if you are interested in seeing more videos like this, please consider subscribing to the Finance Fundamentals channel. Thank you very much, and I'll see you in the next one.